Hello children, once again welcome back to Physics with Sanoop. See, in this video we will be discussing previous questions from the chapter Electromagnetic Waves. See, this is a very simple chapter. You have to understand only two, three things in this chapter. See, a simple formula for the speed of an electromagnetic wave, and see the equation of an electromagnetic wave, and some uses of the electromagnetic waves. Okay, now let's see the first question. In a plane electromagnetic wave traveling in free space, the electric field component oscillates sinusoidally at a frequency of 2 × 10 raised to 10 Hertz and amplitude 48 volt meter raised minus 1. Then amplitude of oscillating magnetic field is. See, we have the speed of electromagnetic wave is E0 by V0, amplitude of the electric field intensity, amplitude of the magnetic field intensity. So, amplitude of the magnetic field intensity will be E0 by C, that is equal to 48 divided by 3 × 10 raised to 8. So, it will be 16 × 10 raised to minus 8 or 1.6 × 10 raised to minus 7. Okay, so this must be the correct option. Okay, now let's see what we have next. The magnetic field of a plane electromagnetic wave is given by, see, this is the amplitude of the magnetic fields. The amplitude of electric and magnetic fields are related such that C equals E0 by B0. See, amplitude of the magnetic field is given, so we can easily find the amplitude of the electric field E0 C B0. Okay, C is the speed of light in vacuum, that is 3 × 10 raised to 8, and B0 we will get from the expression, that is 3 × 10 raised to minus 8. So we will get 9 as the amplitude of the electric field intensity. See, in a progressive electromagnetic wave, electric and magnetic field vectors will be always in phase with each other. So this trigonometric function will be same, exactly same for both electric and magnetic fields. So the expression must be 9, then this one, cosine function. So this must be the correct option. Okay. A radiation of energy capital E falls normally on a perfectly reflecting surface. The momentum transferred to the surface is. Okay, see, the energy of a photon h nu can be equated as mc square, then m is called the equivalent mass of the photon. See, when a photon strikes on a surface, then its momentum is mc as it is directed downwards. Let me take it as minus mc. If it is being reflected from a surface, it retraces its path. Okay, its direction just get reversed. Okay, so the momentum after reflection will be plus mc. Okay, so the change in momentum delta P will be final minus initial mc minus mc, that is 2 mc. See, here we have energy equals mc square and mc will be E by C. So change in momentum is 2 mc, or it can be written as 2 E by C. That is the change in momentum, 2 E by C. Okay. Now see, light with an energy flux of 25 × 10 raised to 4 watt meter raised minus 2 falls on a perfectly reflecting surface. At normal incidence means after reflection path retraces, its momentum gets reversed. Okay, if the surface area is 15 centimeters square, the average force exerted on the surface is. See, mc square, that is the energy divided by time, that is the power. Power divided by area is the intensity. Okay. See, when a photon strikes on a reflecting surface, before collision the momentum is directed downwards and let it be represented by minus mc. After reflection it retraces its path, or the momentum gets reversed, so it will become plus mc. So the change in momentum delta P will be final momentum minus initial momentum, mc minus mc, that is 2 mc. Okay, and here is the intensity. Okay, when this A is taken to the left and one C also to the left, so it will be IA by C. On the right side we will get MC by T. Okay, if you multiply both sides by 2, we will get 2A by C equal to 2MC by T. That 2MC is actually delta P. So let me replace this 2MC by delta P. That is the change in linear momentum. Change in linear momentum by time, that is nothing but the force. Okay, this is the force. So we will get F equal to 2IA by C. Okay, 2IA by C, that is the force. Okay, and intensity is given as 25 into 10 raised to 4. Okay, and see, area, it is given as 15 centimeter square, can be converted to meter square by multiplying with the 10 raised minus 4. And in the denominator we have the speed of electromagnetic wave in vacuum, that is 3 into 10 raised to 8. Okay, and see, 2 into 15, that is 30. Okay, 30 divided by 3, that is 10. This 10 raised to 4 and 10 raised to minus 4 can be cancelled. 10 in the numerator and 10 raised to 8 in the denominator. So it will be 10 raised to minus 7. And we will get 25 into 10 raised to minus 7, or 2.5 into 10 raised to minus 6. Okay, 2.5 into 10 raised to minus 6 Newton. The electric field associated with an electromagnetic wave in vacuum is given by capital E equals I cap 40 cos kz minus 6 into 10 raised to 8t. Children, see, if there is kz, you have to understand that wave is propagating along z direction. If there is kx, wave is propagating along x direction. Now, if you have a negative sign between this kz and omega t, then the wave is propagating along positive z direction. If you have a plus sign between kz and omega t, then the wave is propagating along negative z direction. Okay, if there is plus, along negative direction. If there is minus, then along positive direction. Okay, and see, if there is z, then along z axis. If there is x, then along x axis, like that. Okay, anyway, here we have the value of wave vector k. K is, see, speed of electromagnetic wave is omega by k. So k is called a propagation constant. So k will be equal to omega divided by c, the speed of electromagnetic wave. See, here we have omega as 6 into 10 raised to 8. And c, speed of light in vacuum, that is 3 into 10 raised to 8. So 6 into 10 raised to 8 divided by 3 into 10 raised to 8, that will be 2 meter raised to minus 1. Okay, the oscillating electric and magnetic field vectors of electromagnetic wave are oriented mutually perpendicular directions and are in phase. Electric and magnetic field associated with an electromagnetic wave. The energy of the electromagnetic wave is of the order of 15 kilo electron volt. To which part of the spectrum does it belong? See, we have to find the wavelength. So we have to find the wavelength. If we get the wavelength, we can identify which type of radiation is that. Okay, see, energy of a radiation is given by hc by lambda, where h is Planck's constant and lambda is the wavelength. Okay, so lambda is hc by E. H is Planck's constant, 6.6 into 10 raised to minus 34, and c is the speed of electromagnetic wave in vacuum, and E is the energy, that is 15 kilo is 10 raised to 3, and 1 electron volt is 1.6 into 10 raised to minus 90. Okay, now see, if this is 6.4, see, if this is 6.4, this and this can be divided and we will get 4 here. Okay, then 10 raised to minus 19 and 10 raised to minus 10 raised to minus 19 and 10 raised to 3, that is 10 raised to minus 16. 10 raised to minus 16, when taken to the numerator, it will become 10 raised to plus 16, and 10 raised to 8, that is 10 raised to 24. 10 raised to 24 into 10 raised to minus 34 will give you 10 raised to minus 10. Okay, and 3 by 15, that is 5. 4 by 5 is 0.8. So this is 0.8 into 10 raised to minus 10, or let us say 0.08 into 10 raised to minus 9, or it is 0.08 nanometer. Children, see, this X-ray has wavelength ranging from 0.01 nanometer to 10 nanometer. Okay, 10 nanometer, and this 0.08 nanometer lies in between. So this radiation belongs to X-rays. So this must be the correct option. Okay, see, decreasing order of wavelength. See, infrared, microwave, ultraviolet and gamma rays. Okay children, we have the visible spectrum, that is Vibgyor. Okay, Vibgyor. See, beyond this red we have infrared. Okay, then see we have microwaves and we have radio waves on the right side. See, beyond this violet we have ultraviolet. Okay, this is ultraviolet. Okay, then see, just following the alphabetic order, what we have, see U, V, W, drop it, X, X and Y. Okay, Y stands for gamma ray. Okay, so we want to arrange this in decreasing order. Decreasing order means we have microwaves, okay, then infrared, then ultraviolet and finally gamma rays. So this must be the correct order. Okay, see the frequencies of X-rays. Then gamma rays frequency more than the frequency of X-rays, because gamma rays wavelength is smaller than that of X-rays. Okay, and ultraviolet rays are respectively, see, X-rays A, gamma rays B, ultraviolet C. Okay, frequency increases. Okay, wavelength, see, in this order wavelength decreases. In this order, see arrow, in this order wavelength decreases. Okay, in this order frequency increases. Okay, so A less than B and B greater than C. So A less than B, B greater than C. Okay. Next, which one of the following electromagnetic radiation has the smallest wavelength? Smallest wavelength for gamma rays. Okay. And now let's see what we have. The structure of solids is investigated by X-rays, because the wavelength of X-rays comparable to the interatomic separation. Okay, so they are used to study the structure of solids. Okay,